In this video, we're going to talk more about hypothesis testing. At a bakery, loaves of bread are supposed to weigh 1 pound, with a standard deviation of 0.13 pounds. You believe that the new personnel are producing loaves that are heavier than 1 pound, so you take a simple random sample of 40 loaves. Create a 95% confidence interval. All right, so I just wanted to really remind you, we're not done with doing our state. We will create a 95% confidence interval for the average weight of loaves of bread from the bakery. Our plan is still, we're going to make a 1 here. And again, a T interval is going to be used here because we're taking a sample of 40 loaves. Okay, so if you'll recall, we got to make sure that it was a simple random sample. It says it was. We have 40, I'm going to hope, is less than or equal to 1/10 of all loaves produced. And in this case, our last condition, 40 is greater than 30, so we can move on. So our do, we get this is our interval. If you've forgotten how to type that in, please go back and watch an older video about that. And then, of course, our conclude. We are 95% confident that the interval from 0.96 to 1.04 captures the average weight of loaves of bread from the bakery. So continuing with this same problem, let's say your sample, let's say you actually found a mean weight of 1.05. Is there evidence at the 0.05 level that the loaves are heavier than they should be? So the first thing we should do is we should state some hypotheses, our null and alternative. Our null is that the mean weight is equal to 1 pound. Our alternative is apparently that it is greater than 1 pound. Now, the number in both the null and alternative should be the same. The alternative is not making a claim that the new mean is 1.05. It's only making the claim that we have evidence that it's bigger than 1. Besides listing the null and alternative, we should also define our parameter. Mu is the average weight of a loaf of bread. Okay. Now, the p-value for this was 0.009. Okay. Now, you'll see our p-value is below 0.05, and we should say, our 0.009 is less than 0.05. So what that means is our sample is deemed extremely unlikely if the weight really is 1 pound. And remember, the meaning of a p-value, it is the probability of our sample's occurrence, like the alternative's occurrence, if the null is true. And if that's really low, which it apparently is, our idea is that the null is probably not correct. So we would reject the null in this case. Now, what does that mean in context? Well, we usually say then we have evidence that the mean weight is greater than 1 pound. Okay, so again, when the p-value comes out to be under the significance level, okay, this 0.05 significance level, when the p-value is lower than that, we reject the null. If it is higher, we fail to reject. And I kind of think about it this way, that we have this normal curve in our head that for this problem is centered around 1. Okay, it's centered around 1. And we got this sample, which is up here at 1.05. And what we're thinking is there's evidence that this curve isn't necessarily centered around 1 because 1.05 is such an improbable occurrence for the original curve we drew. I wanted to finish this video by just talking about really the inherent risk of making a decision based on sampling. We have something called type 1 and type 2 errors, and you can read them there. That type 1 is reject the null when the null is true, and type 2 is we fail to reject the null when the alternative is true. And this is just kind of an inherent risk we take when we base a decision off of sampling. For the example I just did with the loaves of bread, maybe if I took another sample of 40, I would get 1 pound, and it's just my sample which led to the conclusion. So that would be an example of type 1 error. It's where we rejected the null, but in fact, if we'd replicated the sampling or done it again, we would have found out we were wrong to reject the null. And that doesn't mean we've done anything wrong in our calculations or finding a p-value. And based on our p-value, we made the right decision. It really has to do with the sample. The sample led us to the wrong conclusion. But the opposite could also be true, where we may fail to reject the null, but in fact we should have. And a lot of times, maybe we have some evidence, but we go through and we calculate and find the p-value, and it isn't below 0.05. That doesn't mean we don't have any evidence. It just means we don't have enough evidence. And maybe increasing the sample size would have led us to a different conclusion. So we may have failed to reject, but in fact, we should have. So sometimes you'll see this presented in a table, and I do kind of like this way of looking at it, that if the null hypothesis really is true, and we rejected it, that is type 1 error. If it's false and we reject it, that was the right decision. If the null hypothesis is true and we don't reject it, that's correct. But if it's false and we don't reject it, that's type 2 error. It depends. People will sometimes ask which one is riskier, and that really is dependent on the individual situation. If it's a drug testing situation, then we maybe are much more afraid of type 2 error. If it's a situation where we're talking about like the criminal justice system, where we consider the null is that they're innocent and the alternative is that they are guilty, then we're much more worried about type 1 error because we don't want to put innocent people in jail. So it's very dependent. The one last thing I want to say about these errors is really just a calculation note. And that is, if you think about the normal curve, think about it for our opening problem with the loaves of bread. Before we do any kind of calculations, we could figure out exactly the weight, the sample mean we would need to cause rejection. And we sometimes call this the rejection region. We could say, well, if you go out there and you get 1.046 pounds, that's going to lead to rejection. That's the point where we'll get a p-value under 0.05. And what that means is that there is 0.05 area in that tail. Okay? Now, here's the thing about like type 1 error. There is a chance, a 0.05 probability of being in this tail if the normal curve really is centered around 1. But being over here in this blue area would have caused a rejection because we set this up. We said, well, what sample mean will do it? So anything in here would have led to rejection, but in fact, very well could have been part of this curve centered around 1. So the probability of type 1 error is always equal to the significance level, which we usually use this little alpha for. So in our previous problem, if you said, well, what's the probability you made a mistake at type 1 error? It's 0.05. So just pay attention. It really has to do with the normal curve and where we put the cutoff, and that's why the type 1 error is always the significance level.